Good evening, everyone. My name is Renu Raman Sahu from the Department of Instrumentation and Applied Physics, Indian Institute of Science, Bangalore, and welcome to the course on Plasmonics Fundamentals and Applications. Today we are going to learn about the permittivity of free electron gas. Before we begin, let us have a quick recap of what we did in the last class. In the last class, that was basically the introductory class, what we did was we looked at metal dielectric interfaces, and we told that this at the interface of metal and dielectric there is uh, there is a field enhancement, and if we bring two metal dielectric interfaces together, we have kind of a field enhancement which has a lot of applications, and there are many researchers which goes on to do this, because at this metal dielectric interfaces we get lot of interesting phenomena. So one of the phenomena which we looked at quickly was this. So here what we are seeing is that as you stretch the material, it is changing its color, and yeah, you can see, and when you relax it back, it comes back to its own color. So what is happening is here, so here again that same phenomenon is happening. So what you see is this metal dielectric, so these are basically gallium metal. So this is one of those like these two are two slides from my own research, where we're able to place these two metals very close by, and as we stretch this material, the gap between these particles, that will increase, and that leads to this change in color. So so you see how interesting this interfaces, that metal dielectric interfaces. So to understand that, what we did in the last class, we started with the Maxwell equations. So let us go. So this was just to motivate you that why studying this is quite important. And so this is just one application that I have worked on. There are a lot of other applications that other researchers has worked on. For example, it can be used to do something called surface plasmon polarity, or localized gap plasmons. So there are a whole lot of other applications in, for example, in cancer treatment. So there are multiple applications you can think of, and for now what we will be focusing on is the basics of it. So what we did in the last class, we started with the Maxwell equations. So okay. We started with the Maxwell's equations. There are four of them. So the first one is the Gauss divergence equal to rho external. Remember that we had defined these fields, so these sources, as external and internal, and we didn't describe them as or we didn't distinguish them as bound and free sources. Okay, so the four Maxwell's equations are this. We started with this. Curl of H is equal to J external plus time derivative of displacement current, and curl of E so this is basically the Faraday's law, this is Ampere's law, this is Gauss law. Okay, and then we told that when there is an electric field E, the material will induce a polarization, and to capture the effect of the polarization, so what is polarization? It is nothing but the dipole moment per unit volume in the material. And this is related to the field. So what would be the displacement field D? So that is related to the polarization that is induced in the material, and the electric field E, and that is related by this equation, by this relation. And then we had assumed that it is a linear material. For linear material, linear material, P is nothing but epsilon naught, and we introduce something called chi. Chi is the electric uh, the electric susceptibility, and when we put this thing in, so what we have is D is equal to epsilon naught E plus epsilon naught epsilon E, which is nothing but epsilon naught 1 plus chi E. Okay, and what is D? D is epsilon naught epsilon E. So this is D. So this is the permittivity, absolute permittivity, or the permittivity of free space. And this is relative permittivity. So when you compare these two, so if we put here epsilon naught 1 plus chi E, what we get from here is the value of epsilon, or the relative permittivity, is nothing but 1 plus chi. So chi, it comes from the polarization. So it is the reaction or the response of the material. What is the material? So any material, there the molecules will get polarized due to the presence of the electric field E, and there will be, so the electric field due to the polarization and due to the original electric field, that will get modified, and it will give to an effective field D. This D is the field that we find in the material, and that field is dependent on this relative permittivity. So this is called a response function. This is a response function. Similarly, for magnetic fields, we can do the same thing. What we can do here is, so for magnetic field, we have, this is magnetic field induction, and it is related to the magnetic field by mu naught mu H, and in presence of some field H, what will happen is the material will try to induce a magnetization. Okay, so what will happen, H, in presence of a field H, there will be a magnetization M. Okay, and so these two are related by, so when there is H, there will be M, and this the resultant of these two will give you B. B is the magnetic field induction, and it is given by this, by mu naught. Okay, so in a linear material, the magnet, or you can rearrange this and write H is equal to B 1 by mu naught minus M. For a magnetic material, what happens is, for a linear material, let's say, for a linear material, B is equal to mu naught mu H. Okay, and M is chi H. So if you put these two, what we get is B is mu naught mu H is equal to mu naught H plus, instead of M we write chi H. So here this chi is different from, so this chi is, we just write a subscript M to show that it is a magnetic susceptibility, and here in general we write E. So what we have is mu naught 1 plus chi M H. For a magnetic material, so basically from here, what on comparison, what you get is mu is equal to 1 plus chi m. And most of the material you see are non-magnetic, and for a non-magnetic material, chi m is close to 0. Chi m is close to 0, which gives you mu is approximately equal to 1. So for most of our cases, we will deal with the electric permittivity, or the electric susceptibility, or the permittivity. So we'll just denote chi e as simply chi. Okay. And then we had further read about, we discussed about we also discussed about some more constitutive relations. So what is the charge, internal charge? The internal charge density, this is given by the time derivative of polarization. No, of the time derivative of polarization, and this was a consequence of continuity equation. And what else we had read? We had read that the internal charge density was nothing but the divergence of P, where P is the polarization. And from the continuity equation, what was the continuity equation? This is divergence of J plus T of rho is equal to 0. So consequence of this is the continuity equation. As a consequence of this, we have this relation J is equal to furthermore, what we have is we had this relation rho total is equal to rho plus rho ext. Similarly, J total is equal to J plus J ex external. So these sets are the rho and the J with no subscript. They are the internal charge densities that occurred as a response of the material to the fields induced by the external external sources or external charges and currents. Okay. And what we have further is, we had seen a relationship between, so this was the final thing we derived out of all this. So all these constitutive relationships, the fields, we have the fields. What are the fields? Fields are D, E, B and H. What are the response functions we saw? Response functions, this can be epsilon, mu, chi e, chi m. These are the response functions. Okay, and these response functions, they relate these fields, and there are further fields like the fields of the metals. These fields are related by the response functions. Okay, and what we had seen are the sources of the field. What are the sources? J external and rho external. So using and we had one more interesting relation that defines the conductivity. So in the presence of electric field, there will be a current density, an internal current density, and that is given by, so more the electric field, more will be this current density, and that is given by this quantity called conductivity. See, there are two relations where the conductivity is involved. One is telling here, conductivity is telling you about what is the current density. There is another relation this is telling you about the charge density. Okay, and remember that this is the internal current density. And in the last class we had derived a relation the uh, between the permittivity E, the epsilon, and this conductivity. Conductivity is sigma as a function of omega. So electric field is related to the external, the total. Oh, sorry, this is to be total. Okay, or this is nothing but rho plus rho external. So this is basically a response function, epsilon of omega, and similarly this is also a response function, conductivity. And you see all the response function there directly relates to the field. For example, the response function epsilon is, it comes from, this is your D, and J is equal to sigma E. Okay, you see how electric field is related to D. D is the electric displacement and this is the current density. And if you take a divergence of D, what you get is it relates to the the charge density, whereas J is the current density. And we had seen the relation between these two quantities. And what we had observed was that the relationship is so this is what we had derived in the last class. Today what we are going to do is we'll try to build upon this, and so what we have already is the permittivity. So permittivity, it tells you about the material response of the system. So how the material will react to the electric field. Now there are two more important quantities which are the equivalent quantities, which tells us about the response of the material to the incident light. So how do we know that? So there are two things here. So we want to understand the light matter interaction of metal and the metal and light. So the behavior of the material, it is captured by the behavior of material. This is captured by epsilon of omega. Whereas what will happen if you put some light on it? Behavior of light incident on material is defined by refractive indices. Okay, in general epsilon is a complex quantity. Okay, so epsilon omega you can write as epsilon 1 omega plus I epsilon 2 omega. So this is a complex number where epsilon 1 and epsilon 2 are real. Now refractive index is what? Refractive index is also a complex number, and it has a real part and an imaginary part. Okay, so and how, and they are also frequency dependent, and how they are related to, how they are related to the permittivity is, so we will denote this as n tilde. N tilde is nothing but the square root of epsilon omega. Okay, this implies n plus I kappa is epsilon, it is epsilon 1 plus I epsilon 2 and the square root of that. Okay, now it is instructive to find what is n and what is kappa in terms of epsilon 1 and epsilon 2. So let us just do that. So how we are going to do? So we have a square root over here, so we will take the square on both the sides. Now we will expand this. Remember that wherever you get I square, it is minus 1. So what we have here is n square plus 2I and kappa minus kappa square is equal to epsilon 1 plus I epsilon 2. And here you remember that in n tilde, n and kappa are real quantities. Okay, now we'll just do a small rearrangement, and what we have is n square minus kappa square plus I 2 n kappa is equal to epsilon 1 plus I epsilon 2. Now on equating real and imaginary parts, what we have is epsilon 1 equal to n square minus kappa square and epsilon 2 is equal to 2 and kappa. Okay, from here what you have is kappa is equal to epsilon 2 by 2n. So we know that kappa is related to epsilon 2 by 2n, and now what we are going to find is, we'll put this kappa in here and then find what is n in terms of epsilon 1 and epsilon 2. So let us do that. So what I'm going to do, So we'll do a small rearrangement again. What I did was I multiplied by n square all throughout. Now we'll rearrange this to make a perfect square. N square. So I'll bring this to the right hand side. Minus n square epsilon 1 minus epsilon 2 by 2 whole square is equal to 0. So here one trick what I'm going to use is I multiply by 2 and divided by 2. Now, so what I'm making here is a perfect square. So let us do that here. So it is n square minus 2 n square epsilon 1 by 2 plus epsilon 1 by 2 whole square minus epsilon 1 by 2 whole square minus epsilon 2 by 2 whole square is equal to 0. What I did here, I just added this term and subtracted this term. Okay, and the rest of this expression was same. Now n square minus epsilon 1 by 2 whole square. Now you see this entire from here to here this can be written as this. So what I am doing now, this is equal to epsilon 1 by 2 whole square plus epsilon 2 by 2 whole square. Now what we are going to do is to take a square root of this. N square minus epsilon 1 by 2 is equal to plus or minus 1 by 2 epsilon 1 square plus epsilon 2 square, the square root of this. Okay, now what n square is equal to epsilon 1 by 2 plus or minus 1 by 2 epsilon 1 square plus epsilon 2 square. Okay, now we focus on one thing. We have told that epsilon 1, epsilon 2 and k, all these are real numbers, and square of a real numbers are always positive. Or they are always greater than 0. Now you look here, if you consider this negative sign, right, then what will happen? It will be epsilon 1 by 2 minus a quantity which is greater than, so the claim is that this quantity is greater than epsilon 1 by 2. How? Because you see all these are real numbers and square of a real number is greater than 0. So what that implies is epsilon 1 epsilon 2 square is greater than 0. Now in this inequality you can add epsilon 1 square plus epsilon 1 square. Now if you take the square root of this, that will still hold the same inequality. Epsilon 1 square plus epsilon 2 square is equal to epsilon 1 square. If you just take the positive square root, and if you multiply, this has to be greater, so this inequality will still hold. If you multiply with 1 by 2 or 1 by 2, this inequality will still hold. Now you see, if I take this to the left hand side, so if I subtract this quantity, this is a positive quantity, if I subtract this quantity from left hand side and right hand side, what I have here is 0 less than epsilon. So I'm taking the square root of this is epsilon 1 by 2 minus epsilon 1 square plus epsilon 2 square root by 2. What is this quantity? This quantity is nothing but 0 less than n square. If we consider the negative sign, right? If we consider the negative sign, then what we are getting is, if we say that this negative sign is true, then what we have here is n square is getting less than 0, which is a contradiction. So what we have to take? We have to discard the negative sign and we have to take only the positive sign. Therefore, n square is, so from here what we conclude is that n square is nothing but epsilon 1 by 2 plus epsilon 1 square plus epsilon 2 square by 2. Okay, so these are the relationships between the four quantities. Okay, so what we are looking at was the relationship between the refractive indices and the permittivity, the complex, the real and imaginary part of the permittivity. Till now what we had done, just for a quick recap, so we started with a very basic motivation that at metal dielectric interfaces we have very interesting phenomena happening, and there are a lot of researches going on in which we try to bring in metal dielectric interfaces very close together because they have a whole lot of applications, and this is one of the slide from my own work, and we looked at this particular application in which we see this, that if we stretch the material, the color of the material is changing. And why is that happening? Because it is also a result of this metal dielectric interfaces. For example, here you see there are metal spheres here and they are very closely spaced, and when you stretch the material, the interparticle gap changes and that changes the whole optical properties. So this is one of the applications, and in the last class what we did was we started with the Maxwell equations, and from Maxwell equations we talked about the fields, and we discussed about the fields and the response functions and the sources, and and in the last class we had obtained this relationship of the permittivity and the conductivity of the material. We are going to do the same today, and we'll try to relate the conductivity with the Drude permittivity, Drude conductivity. And what we have been doing just now was to relate the permittivity with the refractive index. So why is this important? Is because the permittivity and the refractive index, these are the two equivalent quantities, and but when we try to describe a material or the interaction, so the optical response of the material, it is most suitably given by the refractive index. So that will tell you how the incident light, how much of it will get reflected, how much will get transmitted. The optical response is given by NNK, whereas the material's property, so how the electrons are oscillating in it, what are the What is the amount of what are the bound charges there and what are the free charges there, that is given by this permittivity. And the way they are related is this, and here we just derived the relationships. So this is one relationship and the other is this n square, and we'll slowly derive the other two relationship as well. So this is n square and k square, and this is one relationship. Okay, so these are the relationships that we are going to use later in our analysis of the free electron gas, the permittivity of free electron gas. Here one thing to note is that this kappa is the extinction coefficient. It tells us how the fields decay inside the material, or the optical absorption of the EM waves propagating through the medium. And it is linked with the absorption coefficients of the Beer-Lambert's law. So there is a law called Beer-Lambert's law, and this is very useful in many spectroscopic techniques as well. And it just tells nothing. It is I naught. So what in experiments what they do is they incident some light with some intensity I naught. They put a cuvette here filled with certain material, some colloid or maybe a thin film of certain thickness, let's say Z, and they will measure the intensity here, I, and based on the thickness it is, so what usually is found is e to the I equal to I naught e to the power minus alpha Z. So the intensity, it decreases exponentially, and since intensity is directly proportional to the square of electric field, and electric field decays as E is equal to E naught minus, so it also exponentially decays as kappa. So what we have is E square, if we take the square here, E naught square e to the power minus 2 kappa Z. So I is equal to I naught e to the power minus alpha Z. So alpha here is related to 2 kappa. And for dimensional considerations, what they do is, so this is one unit in which they use alpha, and there are other unit they just multiply with alpha is equal to alpha is a function of omega. Kappa is also a function of omega, and they multiply this omega by c. So this is another relationship used in literature for the absorption coefficient. So basically, since we have this relationship, right, epsilon 2 is equal to 2n kappa it determines, it is related to kappa, and kappa tells you about how the fields decay in the material. So that is why this epsilon 2 determines the amount of absorption in the medium. Suppose in case we have the magnitude in some frequency region, epsilon 1 is greater than epsilon 2, the magnitude of this. Then what we have is, so what is epsilon 1? In the previous slide we just saw, epsilon 1 is nothing but n square minus kappa square. And if this is greater than epsilon 2 is 2n kappa. So that is possible if what we have is, let us divide this by n square. N square is what? N square is a positive quantity, so the inequality won't change. So kappa square by n square, and this has to be greater than 2, so we have divided by n square, so 2 kappa by n, and these are positive quantities. So here you see this inequality will hold if you have kappa by n is very small, then this is unity. This is a very small number. Kappa by n is very small with respect to unity, or in that case this will hold if kappa by n is very small, which means kappa is less than n. So the real part of permittivity will have a greater magnitude than the imaginary part of the permittivity if we have a very high value of the the real part of the refractive index, or the kappa is really very negligible. Okay, so here in that case, if this is the case, then epsilon 1 is mainly determined by n. Okay. So here what we saw, so now we saw the relationship between the permittivity and the refractive indices. Now let us switch the topic, and we will talk about the traveling wave solutions of the Maxwell equations. So till now what we did, till now we defined all the fields, the response functions and the sources, and we saw the different relationships between them, or the equivalent representations between them, and we saw for different material, for example, what is the more absorbing material if kappa is more, what is a non-magnetic material if the permittivity, the relative permeability is 1. So we saw the different response functions, the different sources, and the relationships between them. Now we'll study a similar parallel topic. So now it is traveling wave solution. So till now we are discussing about the Maxwell's equations and the related fields. Now we are trying to actually solve the Maxwell equations, and we'll look at, there are multiple solutions of the Maxwell equations for different boundary conditions, and now we will be focusing on a very particular solution called a traveling wave solution. Maxwell equations in absence of external sources. in absence of external sources. So this is a crucial point to see, mark here, that we want to have a traveling wave solution of the Maxwell equations when we have no external source. That means, so what are the sources we had discussed? The sources was the charge, the charge was the charge density, and it consisted of the internal charge density plus the external charge density, and the current density was also the internal current density plus the external current density. So these are the external sources. Suppose there is a system, we try to inject in some current density and some charge sources. So we are not so we are what we will be assuming from now on, from the discussion henceforth, is rho external is equal to 0 and J external is equal to 0. So under this assumption we will now go ahead. So with this, what are the equations we have now? The equations that we have now, so let us look at the Maxwell equations that we actually want to have. So one equation is this doesn't have source anywhere, the Faraday's equation. This doesn't have any source. The Ampere's law, on the other hand, which is the curl of H is equal to J external plus time derivative of the displacement current. Here what we have is, we want to put J external equal to 0. So all we have is the derivative of, since J external is equal to 0. Okay, so these are the two Maxwell's equations we have now. So now what we will do again, now let us take the curl of the Faraday's equation. So let us do that here. Curl of E is equal to now what we are going to use is, we will try to put in the response function. So now we will use so B is related to the H field as, you see here there is B and there is H. So the relationship between B and H is B is equal to mu naught mu H, and there is E here and there is D here, and they are related as D is equal to epsilon naught epsilon E. So now using this relationship mu naught mu H, what we will have now is curl of the time derivative of mu naught mu H. Now that will be, so what we are going to do now, we can interchange, at least for this type of fields, we can interchange minus 2 by dot T. Even we can take the mu naught and mu out, mu naught mu a negative sign and then curl of H. We just interchange these two operators. Now curl of H, we have this relationship, Maxwell equations. We'll use that Maxwell equation. Curl of H is the time derivative of the displacement current. And now we will use this relationship. D is equal to, so it is minus mu naught mu epsilon naught epsilon to the double derivative of the electric field E. Now we will use the relationship C square is 1 by mu naught epsilon naught, or mu naught epsilon naught is 1 by C square. That is the speed of light. So on using that, what we have is mu epsilon by C square with this negative sign, the double time derivative of electric field E. Now we can further use one more approximation, that the material is non-magnetic. For non-magnetic material, mu is 1. So on using this, what we will get finally is, the final equation that we get is, so this is where we started from, curl of E is equal to minus mu, instead of mu we'll put 1, so we don't have to worry about that, mu over epsilon over C square, the double time derivative of the electric field E. So this part is clear, I hope. So what we have here is curl of E is equal to minus epsilon over C square, double time derivative of the electric field E. Now we will use a relationship, it is a vector relationship, where the curl of a vector field is given by the gradient of divergence of the electric field minus the Laplacian of the electric field. This is minus epsilon over C square, and then the double time derivative of the electric field. Usually this epsilon omega is also, so what we'll do now, we'll take the Fourier component. So if we have electric field E, so the traveling solution, so we can use a solution, this E is equal to E naught e to the power I k dot r minus omega t. This is a traveling wave solution. So this is a wave equation. This is the wave equation. and the solution we get is by putting this answers. So let us put and check what we obtain. So if we take a time derivative here, what we get? A double time derivative. We will get minus I omega. So E naught is just a constant, so we won't have anything. So minus I omega whole square e to the power minus I k dot r minus omega t. What we have here is minus omega square, and this is nothing but your electric field E that you used as an answers. And if we use similarly, you can see that divergence of gradient of divergence of E is nothing but, so I times k dot I k dot E. So what it is? It is k times, and there is I, so you will have I square, which will give minus 1, and k dot E. So there is a dot product of k and the electric field, and the direction of this is along k. Whereas what we get from here, we'll get minus k square E. Here the direction is along the electric field, here the direction is along k. So what does this solution represents is, this solution represents there is a direction of propagation along k, and E is the direction of the oscillation of the electric field. So if we put this in this equation, what we obtain is k minus k dot E. See, k dot E is a scalar quantity, minus k square E is equal to there is this minus sign, so epsilon, so I'll write epsilon as a function of omega because it is a frequency dependent function, c square, and minus omega square E. So what we have here now is k dot E minus k square E is equal to minus epsilon omega square by c square E. Okay, now let us look at the condition when the electric field direction is perpendicular to the direction of propagation. This condition is called transverse wave. So if electric field is perpendicular to k, E dot k will be, or k dot E will be equal to 0. Now this leads us to this equation. So from here what we conclude, from here what we are going to conclude is, so the first term here you see that vanishes, so all we have is minus K square, so this is when this condition is there, transverse wave, K square E is equal to minus epsilon omega square over C square times electric field. Okay, so what we have as K, so this minus cancels, electric field you can cut it out. What we have is K square is equal to epsilon of omega square by C square. So this is the condition for your transverse wave. How the properties of the material is epsilon omega, this is the material property, and how it is relating to the wave number and the frequency of the wave. So that's what it tells. So this tells us about the transverse oscillations of the electric field. Transverse oscillations of the field. Okay, now let us analyze what happens when the direction of electric field is parallel to the, now when electric field is parallel to the direction of propagation, then what we have here. So let us do that in the next page. So the equation that we are trying to analyze is this, the wave equation, K dot E minus K square E is equal to minus epsilon omega square by C square electric field E. And we are trying to see the case when K is parallel to the electric field. In that case, what happens is, so we can write electric field E as the magnitude of E. I'll just write it as E, and the direction is K cap. Okay, and for K, what we can write the magnitude of K and the direction is K cap, right? So the left hand side of the equation becomes, LHS becomes K vector K dot E minus K square E vector. So this K vector I can write as K times K cap, and for K vector I can write K times K cap, and for electric field, so it is E times K cap. Okay, minus K square. For E I can write E dot K cap, E times K cap, but K cap is the unit vector, so I'll just write unit vector in the direction of K. So what we have here now is, you see, this K cap dot K cap is 1 because it is a unit vector, and this K is a scalar, E is a scalar, and here we have a K. So what we have is K square E K cap minus again K square E K cap, which is nothing but 0. This implies the RHS also 0. And what is RHS? RHS is minus epsilon omega square by C square E is equal to 0. Now see, amongst this omega square by C square, they are not 0, they are some non-zero values. Electric field E it is also a non-zero value. This is non-zero, this is also non-zero values. So the only way this can be satisfied is if epsilon omega is equal to 0. So what we conclude from here is that the roots of the permittivity, relative permittivity, so how do we get the roots or epsilon omega? So the roots of the permittivity, relative permittivity, what does that mean? All those omega that satisfies, or all those frequency values that satisfy epsilon omega is equal to 0. At those frequencies you can have longitudinal oscillations. So you need to design a material in such a way that if you want to have an electric field oscillating along the direction of propagation, you need to have the permittivity such that at certain value of frequency the permittivity vanishes. So now we can ask a simple question: can we have longitudinal waves in free space? Can we have it? So if we see in free space, there is no polarization at all. So epsilon is nothing but 1, and 1 is not equal to 0. So for all the frequencies epsilon is non-zero. That is why in free space one cannot have any longitudinal oscillations. Okay, I hope you are able to follow till this. Now let us go towards the, so we have been talking about, we looked at a very particular solution of Maxwell's equation. So what does Maxwell equation tells us? It tells us that if we are smart enough to design a material in which epsilon of omega is 0 for certain frequencies, then for those frequencies we can have longitudinal waves. So it is a design problem now. It is just saying the existence of this longitudinal oscillations as well. So it is just these classical Maxwell's equations which will tell about the exotic phenomena. So this is in our common experience we see that longitudinal oscillations are really not possible. But if we are smart enough to design such kind of material, then it is allowed by the Maxwell's equations. So similarly, what we are going to do later in the course is that we will look at certain solutions at metal dielectric interface, and so those would be nothing but your solutions of Maxwell's equations only, but they will predict this interesting phenomena like surface plasmon polariton and localized surface plasmons and all. Okay, so now let us go ahead and model the electrons in a metal. So we are told that they can be the electrons in a metal, they can be considered as a free electron gas. So in so if that is the case, if a metal can be approximated with a free electron gas, then the dielectric function of that free electron gas should also tell me some properties of the metal. So let us go and decide and derive the dielectric function. So what is the motivation for this is that over a very wide range of frequency, so by wide frequency range, what I mean is from the lowest frequency or just the DC electric field to then you start on increasing the speed of the frequency of the oscillations up to visible, then ultraviolet and more. So till ultraviolet or more or higher frequencies, the optical properties of a metal can be optical properties is mostly in the visible and UV region. Uh, the optical properties of the metal, it can be fairly described by the free electron model. Optical properties of metal. And that free electron is also called a plasma model as well. So this is one of the motivation why we want to find the why we want to find the dielectric function of free electron gas instead of a metal directly. The second point is that, so what is this plasma model? This plasma model is nothing but this, it is the, so plasma is nothing but a gas of charged particles, and here in this case the charged particles are electrons. And what we will assume is that this gas of free electrons will have a number density n, and it moves against of number density n, and it moves against a background of positive ions. For example, if you take a metal, it's a sodium, so there are sodium ions, and the free electron, that is that s orbital electrons, it is moving around freely. It moves against a background of positive ion cores. Most of the alkali metals, they are easy to, they really follow this free electron gas model. For example, the sodium, potassium, and so on. Alkali metals, they behave from 0 to, from the DC field to the UV frequencies. It is really very wide frequency range where this free electron gas is followed. On the other hand, there are noble metals, for example gold and silver. They can be modeled by the free electron model only up to the visible frequencies, only up to. Nevertheless, it can be modeled, even till visible it is not a very small range, it is a very wide range. Visible frequencies. So why only up to visible frequencies? Because after that the electrons are not free, so to speak. Why it is not free? Because at frequencies more than the visible frequency, the electrons can go to a higher band in these noble metals. So that is called an interband transition. Because of that interband transition, absorption will take place. That is why you see gold usually it is golden in color. Why? Because of this interband transition, it is somewhere around 500 or a little more than 500 nanometer wavelength. So gold is yellow in color, copper is reddish brown in color. All this phenomena is happening because of this interband transition, and the plasma model is not effective in describing at frequencies above the visible frequency for these metals. So this is called up to visible frequencies due to interband transitions. I hope this point is clear. This is an important conceptual point. Okay. So in this plasma model, what we assume is that we just consider that the electrons are they are oscillating, they are just moving around like balls, tiny balls colliding with each other, and the effect of the ionic cores and the electron-electron interactions are neglected in the plasma model. And another thing is that it is not that we totally neglect the so if you have taken some course on solid state physics, you know that uh, there is nearly free electron model in which the ionic effect of ionic cores are taken into account, and you get a band structure, and the band structure gives an effective mass m star, which is h bar square over where this comes from the band structure. And what we do is, like, instead of taking this lattice potential, so if we consider this lattice potential, instead of treating it in full detail, what we say that okay, there is some electrons and those electrons have some effective mass, and we treat uh, instead of using the effective the mass of electron as the actual mass 9.1 into 10 to the power so m not equal to 9.1 instead of using this mass, we'll use some effective mass, uh, and but we will say that okay, it is still a free electron. So that is how we take this uh, we take into account the band structure, some aspect of this band structure. So what we do is, this is the effective mass, some aspect of the band structure is taken into account by in use by another important point here is that all the electrons are the electrons oscillate in response to the EM field, the external electromagnetic field, and their motion is damped. So once you give some electric field, they will start oscillating randomly and they will collide with each other, and because of that collision their motion will get slowed down. So this is a frequency and it has a unit of 1 by tau, where tau has a unit of time, and this tau is also called the relaxation time. So this tau has another interpretation also. Tau is the average time for which the electron can move without colliding with another electron, and for typically it is at room temperature. Tau is of the order of 10 to the power minus 14 seconds, which gives gamma of the order of 10 to the power 14 hertz, which is nothing but, so you can write as 100 into 10 to the power 12 hertz, and 10 to the power 12 is terahertz. So up to 100 terahertz frequency these electrons can oscillate. So now, so these are the assumptions of the plasma model. Now let us assume that the electrons, they oscillate. The equation of motion in the sea of plasma is given by it is given by the mass m x double dot plus, so we are considering the damping into account, and the electrons are moving with response to this electric field E. This is the motion of electron x and x dot. Okay. Now what is the answers we are going to use? We are going to say that there is a harmonic time dependence of the motion, and the electric field E can be represented as E naught e to the power minus I omega t. This is the driving field, and this is the assumption that again, why we can go for this assumption is that, so the underlying reason for why we can go for this is that the electric field E, or any incident electric field E, they are usually a result of Maxwell's equations, and Maxwell's equations are linear. Maxwell's equations are linear, and because of that linearity, superposition principle is valid. And because superposition principle is valid, what we can do is we can write any arbitrary field as sum over omega E naught e to the power minus I omega t. And we are assuming linear material also here, and since we are assuming linear material, we can add up the response of each frequency. That is why linearity is quite important here, and we can go for this assumption that the driving field has a harmonic time dependence. Now, given that the driving field has a harmonic time dependence, the response is what? The response is the motion of electrons. The motion of electrons will also have an harmonic time dependence. So this is a particular solution for this equation. This we can say as answers. Okay, so here x, the first time derivative x dot is equal to minus I omega x, and the second time derivative and we'll get the second time derivative as minus omega square x. This is what we'll get. Okay. Now let us put these values in the equation of motion. So what we have is mx double dot plus m gamma x dot is equal to minus e a. Driving field is e e naught e to the power minus I omega t, and x is equal to x naught e to the power minus I omega t. So what we have here is minus omega square m x minus I m omega gamma x is equal to minus e. This is what we will get after substitution. Now what we will do is we will take the x along one side, so we will take common. M we took common, minus omega square plus I omega gamma is equal to minus e is equal to the negative sign and x. So x is equal to minus, so the minus minus cancels, e over m omega square plus I omega gamma. So this is how the electron will oscillate in response to the electric field E. Now from this oscillation what we get, so how the bulk of the electrons will move? The bulk of the electron will move as so what we want is the polarization vector. The polarization P is nothing but dipole moment per unit volume. So how do we get that? So number of dipoles per unit volume times what is the dipole moment, right? So for this displacement the dipole moment is I'll write a small p is minus ex. This is your dipole moment. So dipole moment per unit volume is the number of dipoles per unit volume, and the number of dipoles per unit volume is nothing but the number of electrons. So dipole moment per unit volume is equal to, so that is nothing but your P, and that is minus NEX, where N is number of electrons per unit volume. That is same as the number of dipoles per unit volume. Now what we have is, so from here this is a very interesting relationship. So we know that the field D is equal to epsilon naught E plus P, and P is nothing but E plus minus NEX. We know that D is what? D is epsilon naught epsilon E is equal to epsilon naught E minus NE, and instead of X now what we are going to write? instead of x we are going to use these equations here. So minus NA, instead of x what we are going to use is E over m omega square plus I omega gamma. Now what we need is, so here we see an epsilon naught, right? So what we'll do is we'll divide and multiply with an epsilon naught over epsilon naught, so that we can cancel all the epsilon naught from all the sides. So, and the electric field E here is common, electric field E, electric field E, electric field E. So what we have is, if we take so it is 1 minus n e square over m epsilon naught omega square plus I omega gamma. So this is what we have, and you see this is a function of your frequency. Epsilon omega is equal to 1 minus n e square over m epsilon naught 1 by omega square plus I omega gamma. So this is what we have derived. This is the permittivity of, or the dielectric function of the free electron gas. Okay, now what we are going to do is, so what we have here is epsilon omega is equal to 1 minus n e square over m epsilon naught 1 divided by omega square plus I omega gamma. Okay, now what we have here is, let us try to simplify the expression by using, so let n e square m epsilon naught, it will have a, since you see here it is dimensionless, so similarly so that is why, and the denominator here has a dimension of frequency omega square, so this has to be a dimension of frequency square. So let us name that frequency as omega p square is equal to n e square over m epsilon naught. See, it depends only on the number density of electrons. So mass of the electron is constant, E is constant, epsilon naught is constant. So omega p square and the number density of electrons, it is a material property. So omega p square is nothing but your plasma frequency. So on putting that, what we have is epsilon omega is equal to, so this is a material property, this is a very important equation. Is equal to 1 minus omega p square divided by omega square plus I omega gamma. You see here it is a complex valued function. Epsilon omega is complex valued, and we can write epsilon omega as epsilon 1 omega plus I epsilon 2 omega. That will give us the real and the imaginary part of the permittivity. So for that we have to do some more simplifications. So let us try to do that. So what we are going to do, we take this equation, epsilon omega is equal to 1 minus omega p square by omega square 1 divided by 1 plus gamma over omega. So what I'm going to do, I just by omega divided. So this will give me what? 1 minus omega p square by omega square 1 minus I gamma by omega, and then 1 plus gamma square by omega square, which gives 1 minus omega p square over omega square plus gamma square 1 minus I gamma by omega, and 1 minus omega p square by omega square plus gamma square plus I omega p square gamma over omega square plus gamma square and omega. So this epsilon omega is nothing but your epsilon 1 omega plus I epsilon 2 omega. Okay, from here we can separate out the real and imaginary parts. Epsilon 1 omega is equal to 1 minus omega p square over omega p square plus gamma square, and epsilon 2 omega is equal to omega p square gamma by omega square plus gamma square omega. So these are the real and imaginary parts of the dielectric function of the free electron gas. So we will stop here today, and please let me know if there is any difficulty in the steps or any part. So to summarize, what we did today is we looked at the relationship of the real and imaginary part of the permittivity with the refractive indices, and this is just basically different representations of the material property. Then we looked into the travelling wave solution of the Maxwell's equations, and here we saw two modes. One is the transverse mode and another is the longitudinal mode. The longitudinal mode can be only satisfied if we have the permittivity has some zeros or roots. And then we went on to discuss the dielectric function of the free electron gas. We discussed about the plasma model and what are the assumptions in the plasma model, and based on that assumptions what we found out is that the dielectric function of the free electron gas. So in the next class what we will do is we'll try to discuss in different frequency regimes. So we see here that the dielectric function of the free electron gas is a function of frequency. Now for different frequencies how this dielectric function behaves and what are the characteristic of metals we are expecting from this particular model that we are going to discuss. If you have any other questions, please let me know.